his background, Michael and I and Shafi were Radcliffe Fellows at the Harvard University in 2017, 2018. And this all kind of started, I was actually studying jellyfish at the time, and started with getting more interested in sperm whales. But yeah, Michael was kind of, when we went to a machine learning working group, started to take a real interest in the sperm whale sounds and seeing it through the lens of machine learning, and really kind of led to the genesis of the project. So really excited to hear this talk now on towards foundational models for graphs.
Thank you, David. And so I should say that I didn't plan to talk at all. So we've been organizing this workshop for 3 years now, and I don't like workshops where the organizers invite themselves to speak. So, and we had last moment cancellation, and Shafi asked, what would you like to hear I talk about? So I said, well, me personally, I'm interested in foundation models for graphs. And surprisingly, I find my name in the program the next day with title TBD. So I scrambled over the last 2 nights to prepare the slides for that I'm going to show. So a disclaimer, you will not hear about whales. So this is more general talk about machine learning, and hopefully, at least for some of you, it will be interesting. So first of all, when we talk about foundation models, right? So even if you have never worked on foundation models, you probably have used them, right? So probably the best examples are ChatGPT for text, or things like DALL-E, which allows you to generate images, both from OpenAI. And the term itself, it goes back to influential paper of many authors, mainly from Stanford from 3 years ago, where they define these big models that emerged around that time, that are trained on what they call broad data, generally using self-supervision at large scale, and that can be adapted or fine-tuned to a wide range of downstream tasks, right? And it was a kind of name that might have been a bit controversial. It was named similar to how you would name a baby, right? So by elimination. So let's call it large language model, but maybe it's too narrow, right? So what about vision models, or what about models for proteins? Let's call it a self-supervised model, but maybe it's too specific, right? So you can train these models differently. What about a pre-trained model, right? Because most of them are pre-trained. So it somehow gives you the idea that everything interesting happens at the pre-training stage, and then nothing interesting happens afterward. So nowadays, 3 years after, we have already legislation that defines actually what are foundation models, right? So this is an example from the US. So it's probably the only definition I'm aware of that also specifies the number of parameters, which is a little bit a weird thing to do, in my opinion, because it depends very much on the specific architecture that people use. And there are similar definitions in the EU and the UK. So we work on graphs, and the interesting question that I would like to talk about today is, are there foundation models for graphs? So the short answer is no, right? So we can end the talk here, basically. But it's not a kind of categorical no, it's kind of no and with a long pause. And I will show you that there are some infant stage foundation models, and the problems are more difficult when it comes to graph. Right? We'll see why in a short while. So first of all, why we're interested in graphs? Basically, graphs are mathematical abstractions for systems of relations and interactions. Practically, it's hard to think of anything that cannot be represented as a graph, right? From very tiny things like molecules to very large things like social networks, right? So you can all represent them as networks or graphs, right? And they arise in all kind of applications of physics and engineering. And there are plenty of papers that appear on covers of important magazines and journals, applications in physics where people use learning on graphs to design new materials, for example, or to model crystals, or to design semiconductors. Or in biology, of course, there is a plethora of different applications. In chemistry, even in pure mathematics. So graph neural networks were used to prove theorems in low-dimensional topology, not theory. Weather forecasting. So DeepMind had a model that is called GraphCast that is using graph neural networks to predict weather. You can also, maybe with a bit of imagination, to think of whales as a kind of social system, right, of whales interacting. So this is what we are actually trying to get from the birth event that David mentioned. And that's the only slide that I have about whales, by the way. So you can imagine that it can be applied to a lot of different problems regarding animals and the way they interact with the environment, with themselves, and with other species and with us. You can also argue that graphs might be important or essential for artificial general intelligence, whatever it means. And this is a quote from Jay Forrester. So he was writing about mental models, that what we carry in our head is just a model, and nobody imagines all the world or a country. He only selects concepts and relations between them, right? So these are exactly nodes and edges in the graph, right? If you were abstract them in this way. So we also use this concept of knowledge graphs, right? So in principle, you can summarize all the knowledge of the world in the form of these relations between entities, right? So you can say, for example, that I can have entities like Da Vinci, right? And an entity Mona Lisa, and they might be of different types, and the relations, for example, could be that Da Vinci painted Mona Lisa, right? And these graphs nowadays, like Freebase, have billions of nodes and edges, right? So they can capture literally everything that we know. So the type of tasks that we are interested in, we can prototype them in these three different types. So if I give you a graph, we can try to predict the property of the entire graph, right? This is very common in chemistry, in biological applications. So imagine that you have a graph that represents a molecule, and you want to predict its properties, right? So in virtual drug screening, this is a very common task. I would like to computationally predict if some compound would be toxic, would be efficient against the target it is applied to. And this actually has been used and is being used by pharma companies. So the famous result from the group of Jim Collins at MIT a few years ago was predicting computationally a new class of antibiotics. And actually they tested it experimentally. So I think it was the first time in the last 40 years that somebody has discovered new antibiotic compounds. So this is very important. This is very practical, and people are also making millions, if not billions, with at least potentially with this type of learning applied to drug discovery. The other type of problems are node classification. So we are given a graph and we want to say something about individual nodes in the graph, right? So typical applications are in social networks. Imagine that we have social networks and some users are not good users, so they are spammers or they spread misinformation. So we'd like to detect them. And together with my students, we sold 5 years ago a company to Twitter that was trying to do exactly this. So we're trying to detect misinformation on social networks. And we also worked on other, I spent 4 years at Twitter. We also worked on other problems such as recommender systems, which can also be posed as problems in graph learning, where you try to predict edges between the nodes of the graph, right? So imagine that nodes represent users, and I would like to predict whether one user should follow somebody else, right? So this is often called link prediction or link completion in graph learning. So there is another class of problems that I will not discuss today. These are generative models for graphs. So same way as you can generate images with programs such as DALL-E, you can also generate new graphs. For example, you can generate a graph that represents a drug molecule that binds to some protein targets. So you can generate proteins in this way. Again, it can be used for theoretical applications, and we've done a bunch of works in this domain. So here are actually experimental results of binders that we designed for the spike protein of SARS-CoV-2 virus that caused the coronavirus pandemic. And probably the most famous example recently, a generative diffusion model, is from DeepMind AlphaFold 3 that can generate new protein structures. So another important difference that we need to make between different settings of these learning problems is between inductive and transductive learning. So in the transductive case, you are given a graph and you might not know some of the labels of this graph. So you try to predict some of these labels, but you always have the knowledge of the graph and some of its features, some labels and so on. We'll define it properly in a few minutes. In the inductive setting, I show you a new graph that I have never seen before, and I would like to apply now my trained model to the graph that I have never seen before. And you can apply it for node level tasks or to edge prediction and all the zoo of different settings that we've seen before. Now, one thing that is very important when it comes to graph is the very first question is how you actually represent a graph, right? So how do you apply machine learning model to a graph? So imagine that I give you something like this, right? So this represents a molecule, actually a very favorite molecule of mine. So this is caffeine, right? So we all need it probably. So here nodes represent atoms and edges represent chemical bonds, right? And I can take the types of the atoms, encode them in some way, and parse them into a vector, and use it to feed it into a neural network model and predict some properties of this molecule, right? So the question is, how do I order these atoms, right? So is there any particular order? So in fact, I can permute them in any way, and what I want to guarantee is that the property that I predict doesn't depend on the order in which I feed this information into the neural network, right? In other words, what we call permutation invariance. And this is a very important property because in most cases, the graphs do not have any canonical order of the nodes, right? So the nodes come in arbitrary order. So let's consider a few simple cases, right? And we'll see actually some of the difficulties that we will encounter when we talk about foundation models, right? So in a simple case, we consider undirected graphs, right? So mathematically, a graph is a collection of nodes and edges. We assume n nodes indexed from 1 to n. The edges are undirected. Basically, it's unordered pairs of nodes. And we assume that each node is equipped with d-dimensional feature vector that they denote by xi, I being the index of the node. Okay, so as we've seen, the ordering of the nodes is arbitrary, right? So I can order in some way the nodes of the graph, and then I can represent the features as a matrix of size n by d, right? So every row here is the d-dimensional feature vector associated with the node, and then the structure of the graph can be represented as the adjacency matrix, right? So in position ij, I will have a 1 if there is an edge connecting nodes I and j, and 0 otherwise, okay? So because we assumed some order, the order can be anything, right? So I can represent it by a permutation matrix. So I can permute my order of the nodes, and these two matrices, right, the feature matrix and the adjacency matrix, will need to be permuted accordingly, right? So I denote this permutation by Greek pi. It's a matrix of size n by n, right? And here are different possible permutations. So when we talk about learning on graphs, basically we are saying that we want some way of computing functions that take the graph as input. And the two types of functions that we are interested in are those that respect these permutations. So the first type is what we call permutation invariant functions. So no matter how I permute my inputs, the output should be the same. The second type of functions are functions that change in the same way if I permute the input, right? So the output has the same structure as the input. So if I permute the input, the output changes exactly by the same permutation matrix. This is what we call permutation equivariance, right? So let's look at the simple problem of semi-supervised node classification. So I give you a graph that looks like this. And sorry, that you might not see it very well, but here we have the adjacency matrix of size n by n, the node feature matrix of size n by d. We have some known labels. So we have the labels of nodes 2, 3, and 5, right? And we want to predict the unknown labels, right? So it's a graph with a few missing labels, and we know the features. So the first thing I can do is to completely ignore the features, right? And what I can say is that if I know the labels of a few nodes, let's try to somehow guess the in paint the remaining labels, right? So I will try to propagate the labels on the graph, and this way I will guess the labels that I don't know. And the way to do it, we can actually use ideas from physics, which are called diffusion equations, right? So diffusion equations were studied in ancient times by Isaac Newton. He famously designed an experiment where he formulated what nowadays is called the Newton law of cooling, that tells us that if you take a hot body and you put it in cold environment, then the rate at which it will be losing its heat, right, or its temperature will be changing, will be proportional to the difference of the self-temperature, the temperature of the environment. Right, so this is a very general principle. You can apply it to anything, to chemical diffusion. You can apply it to propagation of rumors on a social network, right? So here we see a version of this law on a graph, right? So what is written here is the temperature, right, or some quantity at the nodes of the graph. I denote it in continuous time t, right? And what you see here is the self-temperature, right? So that's the quantity at the node itself. The temporal derivative is the rate of temperature change. And what is written here is the temperature of the environment, right? So that's the average of the temperature of the neighbors. So if I reorder slightly the terms in this expression, what I get here is the graph analogy of the classical gradient operator. And what I get here is again the graph analogy of the divergence operator from classical calculus. Together, the divergence of the gradient is called the Laplacian operator, right? And we get a very simple heat equation that you're probably familiar with from basic course in partial differential equations. So what we also know that this is a prototypical example of gradient flow. So it's a special type of differential equation where the evolution goes in the negative direction of the gradient of some energy. And in this case, the energy is called the Dirichlet energy. It measures the smoothness of the node features on the graph, right? In other words, how similar I am to my neighbors. And it decreases with time, and in the limit, it converges to zero, right? So in the limit, everything becomes constant, right? So basically, the heat diffusion makes the temperature constant everywhere. So we can try to apply this idea for our problem, right? So I remind you, we have some known labels on some subset of nodes, and we want to guess the labels of the unlabeled nodes, right? And we can try to use the known labels as the boundary conditions and diffuse this information. So we run the diffusion equation. We start with, in this case, one hot encoding of the labels, right? So 0 and 1. So that's a delta probability. And we run this one iteration of this diffusion equation, two iterations of this diffusion equation. After 3 iterations, we can just decide, right? So we get some probabilities, so we can just say that if it's bigger, then I will say that this is green label, right? So I'm guessing my labels in this way. And if we write it mathematically, we can write it this iterative equation, and the boundary conditions are encoded by just looking at the submatrix of in this equation, right? And we actually write the limit as in closed form, so it's given by some matrix inverse. And this is a very simple idea. It works well in many situations, and the assumption under which it works well is that the graph is homophilic. So if my neighbors are assumed to be similar to myself, then this idea works very well. And what is important, there is no learning whatsoever, right? So I just give you the labels, and I run a deterministic procedure, and it converges to some answer that is reasonable only in some cases, right? Under the assumption of homophily. If the graph is not homophilic, which is most of the interesting cases, we need to do something more interesting. And here we can use graph neural networks. So again, I remind you, the setting is that we are given a graph with a few nodes that are labeled. We now would like also to use the node features. So what we want to do is to compute some parametric function that predicts the unknown labels in the unlabeled nodes. And now it will be a function that takes as input the structure of the graph, the features, and it has some parameters, right? The weights of the neural network, and that's what we want to tune. So we train the neural network by minimizing some loss. Typically, it's cross entropy between the predictions of the model and the labels of the known nodes. And using these optimal parameters, we would like to now apply the inference on the unknown unlabeled nodes, right? So how does this model look like? So graph neural networks, most of them operate by means of message passing. So what is meant by message passing is that every node looks at its neighbors and receives some information from these neighbors, right? We call these messages. So this is some function that takes as input the features of the node and the neighbor, and sends this message to update the features of the node itself. Now, what is important that we don't have canonical ordering of the neighbors. So any way that we aggregate this information must be permutation invariant, right? For example, we can use the sum or the maximum. So depending on the choice of this aggregation operation, we can distinguish between generic message passing, attentional architectures. So the most famous instance are transformers, right? So you can see transformers as a special type of graph neural networks operating on a complete or fully connected graph with some extra stuff, which is positional encoding, or convolutional architectures that I would like to consider here, which basically the reason of the name is that when your graph is agreed, this architecture boils down to the classical CNNs that you use in computer vision. So if I were to write it as matrix equations, basically convolutional architectures look like this. So we have the feature matrix and some constant matrix that is independent of the features that applies to it to do the propagation of the features on the graph. We can also say some theoretical claims. So under some technical conditions, we can upper bound the expressive power, right, or the kind of functions that we compute with message passing by what is called the Weisfeier-Lehmann graph isomorphism test. So basically, what it tells you is that certain things cannot be computed by message passing. So let's look at this simple convolutional neural network. So it's a single layer that looks like this. So I sum the neighbor features that are transformed by some linear transformation, right? This matrix W that is shared for all the nodes, right? So this is a very simple thing. In matrix form, I can write it like this. So I have the node features. I multiply them from the right. So the size of this matrix is D by C. D is the dimensionality of the features. C is the number of classes. And from the left, I multiply by a matrix of size n by n, right? So this is the diffusion or the convolution operation. So slightly different way to look at it is I can pre-compute the diffusion, right? So I get the diffuse node features of size n by d. And now at every node individually, I apply linear classifier. So that's exactly what is written here, right? So basically it's classifier applied independently on every node of the graph. So as this or a convolution operation, I can use many different things. It can be the adjacency matrix of the graph. It can be the graph Laplacian. It can be polynomials with respect to any of these. It can be rational functions. It can be even more exotic things like motif Laplacian. So if I have directed graphs, I can count occurrences of some subgraph structures and then reweight the graph, make it into an undirected graph. And basically this way, I account for the presence of certain structures in the graph. Bottom line is that it doesn't really matter. It all boils down to the same type of equations. But here comes the problem, right? So imagine that I did everything that I described you before, right? So I pre-trained this GNN, and now I would like to apply it to a new graph, to a graph that looks like this, right? Is it at all possible? So in the new graph, the number of nodes is different, right? So we have n, here we have n prime. The dimensionality of the features may be different, so it's d prime. The number of classes can be something else, right? C prime. So everything is different, right? So the features that are known also different. So I cannot even correctly write it mathematically because the sizes of the matrices are not correct, right? So if I try to apply this W star, the optimal weights of the neural network that I computed before, just doesn't fit, right? So here it's D prime, here it's D. The output should be C prime, and it's C. So right, it doesn't work. I must apply it only in the case where everything is the same, right? So the number of classes is the same, the dimensionality of the features is the same, and therefore this kind of approach would be limited only to these settings. Okay, so we'll get back to this example. It was a simple example just to visualize why graph neural networks are problematic and cannot be used as is as foundation models, right? So let's look now at knowledge graphs, right? So I showed you the example. So what is a knowledge graph? Basically, it's these triplets of a pair of entities and relation between them, right? Like, for example, we usually call them head and tail. So these are directed graphs. So the head could be, for example, Da Vinci. The tail can be Mona Lisa. And the relation could be of the type painted, right? So the typical type of problems that we want to do with knowledge graphs is either entity prediction or relation prediction. So for example, I have a header in relation, and I would like to predict the tail, right? So I would like to ask Da Vinci painted what, right? I would like to predict which paintings Da Vinci painted based on maybe a few examples of his output, right? Or I want to predict the relation. So I have Da Vinci and Mona Lisa, and I would like to predict what is the relation between. Did he burn it? Did he cut it? Or maybe he painted, right? So of all possible relations, I would like to predict the right one. So there are many ways to do it. The classical example or the class of architectures for embedding knowledge graphs is called Trans-E. And the idea is that you find d-dimensional representations, or basically represent your entities and relations in the same space as vectors in a way that at least approximately they add up like this, right? So if I take the head vector and add to it the relation vector, I get the tail vector, right? So the embedding is constructed such that this relation is is satisfied approximately, right? And again, there are many versions of these algorithms, but basically what it allows you to do is to do this form of arithmetic. So if I know that Paris is the capital of France, and I can ask the question, which country is Rome capital of, right? So I will add the representation of this relation to Rome, and it will land me at least approximately in Italy, right? So something like this. Basically, it's a transductive setting because here we have a known set of entities and a known set of relations, and I'm answering questions of the form, I give you H, I give you R, and I want to see the T, right, the tail. Now, in the inductive setting, I might have a situation when I have a new entity, right? For example, Berkeley, right? I didn't have it in the training set. What would I do now, right? I don't have the embedding. I don't have the vector representation of Berkeley, right? So with this approach, I cannot do it. I need to retrain everything from scratch, right? It can be also another situation where we have new entity and new relation. For example, I would like to say Berkeley was built in when, which year, right? So I also cannot do it with this approach, right? So basically, the conclusion here is that we have here an absolute representation of entities and relations, and this precludes generalization. So it only works for a given graph, right? So this is actually still very useful. So Twitter, for example, was using trans-E type of architectures to represent a lot of graphs with billions of nodes and multiple billions of edges. It is very useful because now you can compare them as vectors, right? So you can do tasks like link prediction, but you see that it is limited. So if a new node comes, you cannot deal with these situations. Now, if you look at how humans do reasoning, we tend to compose different types of relations, right? So let's do a little exercise in family relations, right? So let's say this is a family graph, right? So this is me, and this is somebody in my family. And can you tell me what is the relation between me and this person? Anybody who can guess it from this graph, right? So again, the relation is so an entity, a family relation, and another entity, right? So this is my son, for example, right? So who is this? Right, granddaughter, right? So how do we know it, right? So I can look at the following path. So it's the daughter of the sister of my son, right? So this is granddaughter. Is it the only possible answer, right? So I have a path that takes me from one node to another. So this is another version, right? So it's the daughter of my wife, right? So this is also a granddaughter, right? Or another possibility could be the daughter of the sister of the son of my wife, right? So basically, the conclusion is that basically using different paths that take me from one node to another, I can produce meaningful relationships, and this smells very much like message passing on a graph. And this was the idea of the neural Bellman-Ford architecture that was developed 3 years ago at Mila in the group of Jian Tang. A really beautiful work. I don't have time to explain why it is related to Bellman-Ford algorithms in dynamic programming. But basically, the idea here is following. So imagine that we have, again, the query of the type the head, the relation, and we try to predict the tail. So we use here what is called the labeling trick. So we initialize the head node feature with learnable relation vector. So basically, everything here is set to 0, but the node that I'm interested in, I put their information about the relation. So I condition on the relation that I'm trying to predict. And now I do message passing on the graph. So I propagate this information in the graph. And this, if everything is designed appropriately, produces the probabilities of every node to be the tail, right? And I can use this input to predict the tail node probability that is conditioned on the relation and the head, right? And this will produce me, in this case, the highest probability is obtained here. So I can establish this relation, right? In this case, the relation of being granddaughter of this node to be the green one, right? So basically what it does is it creates entity representations that are relative. So if I have this knowledge graph, I have Michael Jackson that authored a song that is called Thriller, and the song was of the genre disco, and Michael Jackson also collaborated with Quincy Jones that also worked in this genre, then I can probably make a prediction that Michael Jackson worked in the genre of disco, right? So the representation that I will obtain here will be relative to the node Michael Jackson, right? So it will not be an absolute representation. It will be a representation that will be different for every node in the graph. And what it allows me to do is to transfer this model to a different node, right? So now I have an entity representation that is relative to another node, for example, the Beatles, right? So I can see the same pattern, but now on a different part of my knowledge graph, right? And basically, this relative entity representation is what allows to transfer to new entities. Okay. So to summarize, we've seen two methods. So a classical method that relies on absolute representation, such as trans-E, can work only in transductive settings, right? So it predicts known relations between known entities. It cannot generalize to new entities and cannot generalize to new relations. This idea of neural Bellman-Ford learns only relational embeddings. So it can generalize to graphs with new nodes, right? So in other words, it can work in inductive settings with new entities, but it cannot it cannot work with new relations, right? And we actually want both, right? So imagine that we have two knowledge graphs. So one, for example, taken from Wikipedia, another one taken from Freebase. So they might have different ways of representing relations. They might have different naming for relations. So everything might be very different in these graphs. And we want still to be able to train our model on one and then apply to another, right? So this brings us again to the question how we build graph foundational models, right? And again, maybe in line with our first definition of what we call foundation model, it's a model that learns transferable graph representations that can generalize to new previously unseen graphs, right? So this is how we define graph foundation models. And the main difficulty, so this is the discussion from recent position paper that will appear at ICML. The key difficulty in designing graph foundation models lies in the fact that we don't have necessarily the same representation space, or it's difficult to find it. So in computer vision or in natural language processing, we always have some shared vocabulary that defines the basic units in a particular domain that can be transferred across different tasks and data sets. And it's not clear what are such basic units and what is such vocabulary for graphs, right? So as an example, if I use language, right? So I take a phrase like graph foundation models are hard, I can represent it in a dictionary, right? So these will be my tokens, right? And every text in English can be represented in this way, right? So I have basic units. The dictionary may be very large. It might contain potentially millions of such units, but they are fixed, right? In case of images, same thing, right? So I can take an image like vision transformers do, decompose it into patches. And again, I might have a lot of different patches, but every image can be represented like this. With graphs, it's much more difficult because in graphs, first of all, we have a lot of different problems that involve graphs, and the graphs can look very differently, right? So for example, in case of node classification problems, as we've seen, we might have one large graph with node features and some given node labels, right? Like in social network where we try to detect spammers. In the case of knowledge graph reasoning, we might have one large graph without any node features or node classes, but we might have meaningful edge types, right? So these triplets of head, tail, and relation. In other applications such as graph classification and regression, so this is what we see in problems in chemistry and virtual drug screening, we might have many small graphs with graph level labels, right? So for example, a molecule and its physical properties. And the ideal dream foundation model should be able to work across all the possible applications, right? So it should be able to work with big graphs and small graphs and predict node level outputs, edge level outputs, graph level outputs, right? And of course, it's wishful thinking, and such models do not exist yet. So what could be potential candidates, right? So we've seen that classical GNNs, they only work on graphs where we have the same feature type and dimension. Graph heuristics such as label propagation or other things like page rank, for example, they work only in special cases where the graph, for example, is homophilic, and they don't involve any learning, right? So we can hardly call them foundation models. We can use LLM-based approaches, right? So basically, LLMs are very powerful, right? So let's parse a graph into something that will look like a sequence in language. But it's limited to cases where features are discrete or you need to discretize them. And they also break the graph structure by parsing it into a sequence, right? And many important properties are lost. And it's also not clear whether they're scalable, right? So can you, for example, parse into a string a graph that has a billion of nodes, right? So probably not, right? We have not tried. But they look cool, so I'm saying it maybe with regret that I don't think that this is the right way to go, but we also had papers in this direction. So this is one that was also collaboration with the group of Jian Tang, a model that is called graph text. So basically here we have graphs that are represented as some kind of using some parser, and now we can ask all sorts of questions. So for example, you get few shot demonstrations. So you get, for example, patterns like this. So this is my central node, and these are the labels of the neighbors that are ordered based on the personalized page rank, right? So my node is of type F, and the neighbors are all A, right? In another example, the node is of type G, and all the neighbors are G. And another example is the node is of type B, and then all the neighbors are B, right? And here is the question. I give you a node G, and the neighbors are A, G, A, E, and you need to predict what type the node is, right? And we use a pre-trained model like ChatGPT. So, and the answer is that central nodes are vital. The answer is G, right? So basically based on the node itself. And here the user corrects it. So he says that page rank labels are ranked by importance, with the first one being the most critical, and asks the language model to reevaluate the prediction. And then it, based on the first PPR label, it answers that the correct answer is A, right? Which is the correct answer here. Okay, but basically you can interact and you can reason about graphs. So these models are powerful, but again, all the issues that I mentioned before still apply, right? So they probably don't scale. You break the structure of the graph, and then it applies only to limited cases. So I would like to show you today two recent works. So I think we can distinguish between three types of what can be roughly called foundation models for graphs, right? So these are either task-specific models, for example, applied in the domain of chemistry, right? They could be based on LLMs, right? Like we'll call them proto-graph foundation models, but they also can be task-specific. So they can, for example, apply to relational graphs or to node classification, right? And let's start with with relation graphs, with knowledge graphs. And this is the work called Ultra by Maxim Galkin, my collaborator. So first thing to note is that we already seen permutation invariance. So permutation invariance is very important because basically it allows you to abstract out the node IDs, right? And what it allows the GNNs to inductively transfer the patterns that you learned from the training graph to another graph that you have never seen before, right? Basically to new nodes. And we've seen this example, right? So we had Michael Jackson and Beatles. So if you abstract out the node IDs, basically what you're looking for is patterns of this kind, right? So I will not be looking for Michael Jackson and then I cannot generalize it to another node. I will be looking for a directed structure like this, right? In my graph. So you can also in knowledge graphs we have both nodes and relation types, and they're all ordered in a certain way. So we can allow for permutations of both node IDs and relation IDs, right? So this is something that is called double permutation invariance. And in this case, it ensures that the model can learn structural patterns between both nodes and relations, which allows to inductively transfer the learned patterns to another graph with both new nodes and new relations, right? So basically, if we had to abstract, to increase the abstraction level to abstract from concrete nodes to abstract nodes, now we also abstract the relations. And the way that you can do it is constructing a graph of relations, right? So it's relations of relations. And there are four types that are possible. So if we have, for example, in our example of Michael Jackson, Thriller, and Quincy Jones, so we had author and collaboration type of relation. So in this new graph of relations, the nodes will be the types of relations, and the edges will be the way that they are connected, right? So in this case, two relations can start from the same head, right? So both of these edges start from the head, right? Which in this case is Michael Jackson. We might have, so we call this head-to-head, right? We might have another pattern which is called head-to-tail or tail-to-head, right? So in this case, the tail of one relation can be head of another relation, and that's exactly this kind of structure, right? Or we might have tail-to-tail where two relations have the same tail, right? And this is an example shown here. Okay. So basically you can take any multi-relational graph and build from it this representation. And these four fundamental interactions, right, the relations of relations are universal. So that's the only thing that you can have, right? And by construction, you can show that this has this property of double permutation invariance. Now, what it allows you is to create representations that are relative to the relation type, right? So here we have a representation relative to the genre, right? And we can transfer it to a representation that is relative to a completely different type of relation, right? So you see that we have the same pattern, but it is applied to different entities and to different relations, right? So if we have Michael Jackson that was the author of song Thriller, we have a person called Manuel Blum that was the PhD advisor of Shafi Goldwasser, right? And the same pattern, but different entities and different relations, they're abstracted with the same graph of relations, right? And the representation is relative, and this is what allows us to transfer it to new relations, okay? So the model Ultra, which stands for Unified, Learnable, and Transferable, is a foundation model for knowledge graphs that operates in two stages. So first of all, given a knowledge graph and a query, you build the graph of relations, then you use the graph of relations, you initialize the queried relation as ones and all the rest of zeros, right? So basically d-dimensional vectors, and run a GNN to obtain the d-dimensional relative representations of relations on this graph. So every node here that corresponds to a type of relation will contain these diffuse representations, and then you can use the previous architecture, the neural Bellman-Ford, where the query node, right, which in this case is Michael Jackson, will be initialized with the relative representation of the relation that is queried, which is genre, right? And what you will produce is, again, as before, the probabilities for every node that will allow us to do inductive link prediction. And it works really well. So you can train it on small graphs and then apply it to different graphs that have never seen before. So it works on par or even better than state-of-the-art methods that were applied specifically to these graphs. But with fine-tuning, you can actually get significant gains from this model. So the second type of case I want to show is foundation model for node classification. This is also work that we did together with a group of Jian Tang at Mila. And here we're looking at the problem of node classification. So I remind you what was the problem before, right? So we had a graph with a few labeled nodes and a few nodes were unlabeled. And we looked at this at how to transfer this model from one graph to another, right? And what we've seen is that the simple application of a very simple graph neural network architecture doesn't work because the sizes of the weight matrices do not coincide with the sizes or with the dimensions of the features, right? So we need something that somehow abstracts these representations and doesn't rely on matrices of fixed size. And that's the idea of the architecture. So we use a set of simple convolutional models that can be for which the parameters can be computed in closed form, right? So basically, we have a closed form expression for these W that do not require any learning. And then we have permutation invariant attention that is applied to special type of features, distance features. And we also use entropy normalization that allows to generalize robustly across different dimensions. So basically, this is how it looks like. So we produce these T by T, right? T is the number of outputs of these simple models. Use entropy normalization attention, and the output will be the vector of size C, the number of classes, right? So if in the standard convolutional GNN we find the optimal set of parameters W star by solving an optimization problem, right? So typically cross entropy on the known between the predicted and the known labels. We can linearize this model, and under some assumptions, in particular if the labels have Gaussian distribution, we actually can write it in closed form, right? As pseudo inverse of this matrix F, right? So first of all, you see that the dimensions are correct, right? So the predictions are given in this way, right? So F is N by D, right? So these are diffused features. The pseudo inverse has dimension D by NL. right? And YL has dimension NL by C. So if I now give you a different graph with different features and different labels, everything changes accordingly, right? So I'm not relying on any matrix of fixed size, right? So the output here is given already in the correct form, right? So the dimensions are right. So we don't have the problem that we've seen before. We don't need any training, right? So we don't solve any optimization problem. So it's given in closed form. So we all know how to invert matrices. And the inference has linear complexity, right? So it's efficient and easy to apply this model. So it has the same complexity as the standard GNN. Now, the problem with these linear GNNs is that they're simple primitive models for inductive inference, right? So you can apply them to any graph, but on their own, they may perform poorly, right? So if you compare them to more sophisticated GNN architectures, such as graph attention networks, they don't really work well. So fortunately, what we can do, remember that we could choose the convolution operation. So here we can put more or less anything we want, right? So we can use powers of the adjacency matrices, normalize the adjacency matrices differently. So these are the particular operators that we use, right? So we use these 5, but can be anything else. And now we combine these predictions, right? We have T of them using attention, but we want the attention to be a special type of attention. We want this attention not to depend on the training graph. So what we call inductive attention. And in order for this to happen, we show that it must be robust to transformations of the features and the labels. And in particular, these transformations are permutations and masking of the dimensions, right? So I remind you, these are the permutations that we've seen before, right? So these are permutation of the nodes. Now we have 2 extra types of permutations. We have permutations of the data, right? So I can scramble the columns in my feature matrix, right? By changing the order of the dimensions. I can also scramble the classes of the labels, right? Because there is no particular reason to assume that they must come in any particular order. So the permutation invariance now is with respect to all the 3 transformations, right? So permutation of the nodes, of the features, and of the labels. So the permutation of the nodes is given for granted because by design of the graph neural network, so it's invariant to the node permutation. But the property, the other property, permutation of the data and permutation of the labels is something that we need to check. So for our simple linear model, we can actually see that it is invariant to the node to the data permutation, but it is equivariant with respect to label permutation. So everything is multiplied by this matrix Q. So in order to get rid of the matrix Q, we can look at, for example, product features, right? So if you look at the products of the type Y transpose, we see with a little bit of algebra that this matrix Q, because it's permutation, it's orthogonal, goes away, and product features or distance features of different types are both data and label permutation invariant, right? So the last thing that we need to do is we need to normalize these features properly, right? So we use the distance features because in different dimensions we might have the scale of the features can be very different. So we use entropy normalization that is common, for example, in manifold learning. And these are features that are used to compute the attention. So and the architecture is what is shown here. So we can actually see that it works extremely well. So here's an example. We train this model on one graph, Wisconsin. So it's a small graph with that is heterophilic, and we use only 120 training nodes. So it's a tiny training set, right? And we compare it to standard GNN models where the training set size is something like 500,000 nodes. So we have 3 orders of magnitude difference in the size of the training set. And you see that this model actually works better than the state-of-the-art baselines. And maybe even better way to see it is on this plot. So here we have the average test accuracy on all the 31 graphs. So each of these standard graph neural networks was trained separately on the respective data set. This was trained only on one of them, right? So in this case on the Wisconsin, and this one was trained on archive, which is also a very small data set with very few nodes, right? So that was extremely small training set, and it still works better, right? So I think we can say that we do have a foundation model for the node prediction tasks. So what are the takeaways, or maybe what are the open challenges? First of all, when you compare to the foundation models that we see, we all love and use in practice, is that the data that is available for graphs is order of magnitude smaller than what we have in text or in vision, right? So if for example, GPT-3 was trained on 300 billion tokens, GPT-4, I think this has never been officially stated, but the rumors is 20 trillion, right? By the way, the scale here is logarithmic, so the size of the circles. Otherwise, you would see a tiny dot, and everything else will be bigger than this room. So this is ESM2. So this is a protein language model that was trained on 60 million sequences. AlphaFold 2 was trained on 140K structures. QM9, so this is the molecular data set, has roughly the same number of molecules. And if we look at the open graph benchmark, so this is one of the largest collection of graphs that is available in the public domain. So again, we don't know clearly what we want to look at, whether we want to scale the number of nodes or the edges, or maybe diverse structures, right? So it's not exactly clear, unlike text where we can just say, let's add more tokens, right? So in graphs, you can have graphs with a lot of nodes, right? So this is the largest graph in terms of nodes in OGB, which is a Microsoft academic graph, 240 million nodes. If we are looking at edges, so the wiki knowledge graph has 600 million edges. And if we want to look at collections of different graphs for graph level predictions, PCQM, so this is a molecular data set, has 3.7 million different graphs, different molecules with their chemical properties, right? So I don't have a clear answer what exactly should be scaled, right? So what we see from some examples is probably diversity of graphs. This is what we see from Ultra. This is what we also see from Graph-Any, but this is an intuition, and I don't have a clear answer. We also, unlike graph neural networks, where the model expressivity has been studied to death, whether using Weiss-Lemon formalism or other constructions, we don't have any idea about the expressivity of these models currently. And what we know for sure that different tasks require different types of symmetry, and therefore we need to probably tailor our expressivity analysis to these situations. What is also clear that if we just try to use the most expressive model, it will probably be prohibitively expensive, so it's not a good idea, right? So we need to do some kind of careful trade-off between expressivity and efficiency, and of course, how many samples do we need? How good is generalization? It's all open questions. It is also one of the messages probably that we can see from our discussion today is that absolute information doesn't transfer, right? So we've seen all the methods that were relying on absolute embeddings do not work when we change, for example, the number of dimensions, right? Or we add nodes or add relations in knowledge graphs. It must be some form of relative representation of the information. The situation is different in domain-specific cases, like in chemistry. So there, for example, we have a fixed vocabulary of the atom types or the edge types, right? The chemical bonds. But probably to work reliably, these models need to learn some form of physics, right? So they need to understand the problem in some sense. We don't have yet a model that can generalize across all possible tasks, right? The model that can predict post-node classification, link prediction, and graph classification. And probably the way to have such a model is to frame all tasks as a single task. So you can frame, for example, node classification as link prediction, right? So it looks like link prediction is the most general type of problems for graphs, and probably we should be focusing on these type of tasks and the models for this situation. So that's all I had to say. I want to credit my co-author, Michael Galkin. So he is also famous on Twitter for making T-shirts with different memes. So this was from, I think it was from ICML last year. So he printed a shirt for me with my face on it. And thank you very much. We'll be happy to answer any questions.
Thank you, Michael.
I am curious, one of the how does this perform on some of the classic graph classification problems, for instance, whether a graph is planar or not? which is known to be a hardware?
Good question. So I think standard message passing can test planarity. I think it falls under the device file element. It can. I think it can. I'm not sure actually. So I don't remember. But with these models, they potentially have weaker expressive power because you use relative information. So it might be that it cannot test planarity. So I think this is an open question.
And I have a question about ultra. Is that okay? In the construction of the relational graph, can't you have multiple relations between the second order nodes? Like, you know, the brother of a daughter and the daughter of a brother are not the same thing, and therefore you need to have a number of different. So it becomes a large multigraph, right?
Yeah, it is a multigraph. Yeah.
It is a multigraph.
Yeah. It's not basically also the definition of this relation is that it can be, right. So basically, you might have multiple relations.
So for these multi-relation structures, do you run into problems with like, hey, we have to find this big set of motifs, and that ends up having a non-trivial complexity?
Yeah, so the motifs, well, depends on the size. So the worst case is exponential. But in practice, these motifs are for about 3 nodes. So that's something that you detect relatively easily.
So about the motifs or the unit, do you think that there would be kind of standard generic units that are relevant for all graphs, or is it really dependent on tasks and data and domain?
I think it depends on tasks and data, right? So if you look at, for example, chemical applications, right? So molecules, so organic molecules have very clear, very prominent structures like rings, right? So aromatic rings. So these are cycles and graphs. You can actually show that if you inject this information into graph neural network, you can significantly boost performance. Yeah, but in some other applications, like in social networks, these kind of structures are probably meaningless.
Yeah. So maybe the search for a foundation graph model is futile in this sense because they are so diverse and different.
So that's what makes it difficult. And maybe these models will not be very expressive in the sense that when you try to address all the problems, then you get a model that is kind of does trivial things, like counting neighbors, for example, for the type, right? So it's very basic operations. I think we don't know. We actually don't. I don't know. We haven't looked into, for example, in Graphene, what kind of relations we capture in these models. How that actually looks like.
Last question. You mentioned that in foundation models, a property that is mentioned is self-supervised training. So what's the equivalent? What's the analog here?
Well, you can think of maybe the missing node completion as self-supervised. In the node formation. Yeah. But there is no, not always you have.
But that's a transductive case, yeah? Or
yeah, it's a transductive case.
It's not that you would train on the subjective of completing the node, at least not in the examples that you've shown, I think.
Well, in the example in our architecture, you don't have any training whatsoever.
Right.
The training is only in the attention.
Yeah. So would it make sense to train on completing nodes or completing links?
Potentially, but I don't know how to formulate it.
Okay.
Any other questions?
Can I ask a question from Zoom?
Yeah, go for it, Shafi.
Hi. Great talk. Thank you, Michael. It was a great survey. So just bringing it back to Wales for a second. So we could think of a knowledge graph, right, in this context as well with, I don't know, sperm whale eats orca or whatever. With this, although this is against putting things in a fairly simplistic sense of what the whales are talking about, if it's eating or diving or simple. But I guess it would be a knowledge graph in your terminology. And we could think of our language as well as a knowledge graph with some sort of like actions that people make. And I guess in this work that with Adam and Or, we was trying to say that if two languages are expressed as knowledge graphs, then translating from one to the other would have a lower complexity, or at least a complexity in terms of the amount of data necessary. That somehow is related to the degree of the graph and the number of nodes and so forth. So any thoughts about this simplistic model for language? For functional language, yeah.
I'm a bit skeptical because I think basically the community in NLP, as far as I know, and I'm definitely not an expert, so I'm looking at Jonathan. Basically, what the current state of the art actually has moved away from any hardwired model of the language, right? So this was probably 10 or 15 years ago, and it was trumped by scale, by transformers with trained on a lot of data. But when you don't have a lot of data, then maybe that's a better way of doing it. And it's probably our case where we don't have a lot of data. The question is, do we actually, can we have construct meaningfully these knowledge graphs? I think is another question.
Thanks.
All right. On that note, well, thank you, Shafi, for joining in, and sorry you couldn't be here today. And
I listened to everything.
all right, good. And thank you, Michael.
Thanks.
And thank you, David, again.
So that sums up our third decoding communication in non-human species. We covered a lot of ground, you know, now from emergent communication to dolphins, to whales, to fish sounds, to plant sounds. Yeah, really excited to see where this field is kind of continue to progressing and to kind of understand the latest in the graph machine learning and to vowels and the social networks of whales. So we're hoping to convene a fourth one next year, and it's up for grabs of where it will be. There's some possibilities of Harvard or Oxford or maybe MIT. So so stay tuned on where number 4 will be. And thank you all for being a part of this community, and for my co-organizers, Shafi and Michael, for making this happen. All right, now we could go, hopefully there'll be, we'll go outside and we could just continue.